This is an application of Analytic Element Method, or AEM modeling, that I presented at MODFLOW and More in June 2022 at Princeton University. It is titled PEST and AEM Modeling for Data Acquisition Planning. This presentation will demonstrate some very simple examples of how PEST can be linked to AEM groundwater flow models to plan a field data collection program. PEST has demonstrated strengths for decades in a range of closely related groundwater flow modeling data analyses, including parameter estimation and error estimation, uncertainty analysis, predictive analysis, and data value assessment. But those model analyses are often performed after the data set has been collected and is now being used for final model development. The basic concept I would like to propose is that the various strengths of PEST for data analysis make it a very useful tool for planning a field data collection program, writing a work plan. The basic method I would like to use is this. Suppose you know that you will be tasked with developing a groundwater model for a site, and you know that you plan to use PEST to do that, and you want to make sure the field team collects the right data to help PEST help you. Here is a method you could use. Begin by roughing out a simple AEM groundwater model for your site based on your preliminary understanding of its conditions. In that model, place estimates of the parameter values that you will ultimately be using PEST to estimate for your model. For example, let's say recharge, hydraulic conductivity, and stream bed conductance. Add sampling locations in your model based on where and what type of data you plan on collecting at the site to characterize it. Run your model, and in the model, measure the types of data you plan on collecting in the field at your proposed sampling locations. These could be monitoring well water levels, stream flow rates, etc. Take those observations and give them to PEST and ask PEST to estimate the model parameters you are interested in. These are the recharge, hydraulic conductivity, and stream bed conductance values that you already know because you put them into the model. If PEST accurately estimates those parameter values, then your field program is good. If PEST struggles to give good estimates or reports large uncertainties, then you need to modify your field program. You may need to add wells or change their location or measure stream flow at one or more locations as part of your field program. Let's start with a simple steady-state model of a watershed around your site that you plan to model. This is about the simplest AEM box model you could build. The site watershed area is about 1 mile by 1 mile. There is a constant head boundary on the west, driving groundwater flow eastward toward a lower riverhead boundary on the east. North and south boundaries are no flow. You know from geology or soil type reports that there are 3 hydraulic conductivity zones in the watershed, and there is a central stream flowing from the west to the river on the east, and the stream has 3 segments, and there is recharge over the watershed. So those are the parameters you want PEST to estimate for your model. Hydraulic conductivity for zones 1, 2, and 3, stream bed conductance for segments 1, 2, and 3, and aquifer recharge. To start, let's assume that you have 7 monitoring wells at your site, and you want to give those water levels to PEST to have it estimate your parameters of interest. The beauty of this method is that it only takes less than a half hour to build the simple AEM model, and the model takes less than 1 second to solve. So when PEST iterates 17 times, solving the model a total of 170 times, that can all be done in less than 4 minutes. So we let PEST estimate from those 7 water levels, and it calculates model input parameters. And this is the model result. This looks like a very reasonable solution. And when I examine the model calibration, model heads versus observed heads at the 7 well locations, the calibration looks extremely good. But when we look at the actual model parameter values that PEST came up with, we see that they are terrible. Each blue bar represents the actual parameter value I used originally in the model to create the water level observations that I gave to PEST from which to estimate parameter values. The green bar next to a blue bar represents PEST's attempt to estimate that value. We can see that where hydraulic conductivity for Aquifer Zone 1 is 60 feet per day, PEST estimated 6 feet per day. Where hydraulic conductivity for Aquifer Zone 2 is 80 feet per day, PEST estimated 8 feet per day. Where streambed conductance for segment 2 is 150 feet per day, PEST estimated 15 feet per day. The problem here is, as is well recognized in the literature, that hydraulic conductivity and recharge are highly correlated. What PEST has done here is start with low values of aquifer hydraulic conductivity and streambed conductance. And it found that for any reasonable value of aquifer recharge, the heads were way too high. So it just kept reducing recharge until the head values fell to calibration levels, and then it stopped. This created a situation where both recharge and conductivity, or conductance values, were 10 times too low, but the heads matched perfectly. The fix for this is to find some other observation data that can be measured and given to PEST that breaks the tie or lessens the strong correlation between recharge and conductivity. That measurement is some sort of flux value. In this case, we will use a stream flow measurement. For more information on this concept, see the 2020 Groundwater Journal article by Randy Hunt, in which he describes the application of PEST to the Freiburg groundwater flow modeling exercise from the 1980s. So we think maybe it will help PEST if we can obtain a measurement of stream flow. To do that, we place a stream gauge in our model just at the location where we would propose to measure the stream at our site. We run the model, and this time we measure the 7 monitoring well heads, as we did before, and stream discharge at the mouth of the stream, which turns out to be about 30 cubic feet per second. We provide these data to PEST in our next parameter estimation run. This time PEST does much better. The green bars showing the PEST parameter values are much closer to the actual values. The only place PEST seems to be having difficulty is for the stream bed conductance estimates for stream segments 2 and 3. The uncertainty range for segment 2 is a bit large, and the uncertainty for segment 3 is very large. The PEST 95% confidence estimate ranges from 100 to 1,800 feet per day. PEST is saying it really doesn't know very well what this value is. So I thought about how I might be able to provide PEST with more information to let it better estimate stream bed conductance. We already know the stream stage. It is the reference head values in the AEM model river elements. So I thought that installing piezometers next to the stream to measure aquifer head beneath each stream segment, and also measuring the stream flow in each segment, might help PEST estimate the resistance of the stream bed material in between. So I added 3 piezometer measurement locations and 2 additional stream flow measurement locations in my model, just as I would propose to collect those data in the field. And I fed the monitoring well heads, piezometer heads, and stream flows to PEST for parameter estimation. This helped to greatly reduce the stream bed conductance uncertainty, but it was still a bit larger than I liked for stream segment 3. So I decided to put 1 more piezometer along that segment. I added the piezometer measurement location and then fed all of the observations to PEST. PEST did a very good job of estimating site parameters with a high degree of accuracy and a small amount of uncertainty. So I wrote up that sampling work plan and submitted it to my boss. But he said that the client was cost sensitive and that it would cost several $1,000s to install each piezometer. So he asked me if I could get by with 1 less piezometer. From my work with PEST to this point, it appeared to me that the piezometer in stream segment 1 was not crucial, so I removed it and I fed this reduced observation data set to PEST. PEST produced almost identical parameter estimates without the segment 1 piezometer. That allowed me to finalize my work plan. Now this is an example where we were able to generate good estimates on site characterization parameters without even doing an aquifer pumping test. There was no need to get 1 or 2 rigs in the field and perform 24 or 48-hour pumping tests. The watershed response to recharge, with resulting groundwater levels and stream flows, allowed us to estimate the hydrogeologic parameters. But suppose you were asked to plan an aquifer test and to determine the best observation well locations. That is what we are going to examine in the next example. Suppose that you have developed a very simple AEM box model for your site. Your site consists of an aquifer area about 1 mile by 1 mile with a buried channel sands deposit running from west to east near the central area of interest at your site. You plan to conduct a pumping test at this well with transient drawdown measured at observation wells, and you want to estimate the hydraulic conductivity and specific yield of the main aquifer. You also want to estimate the hydraulic properties of the channel sand deposit. And your conceptual model tells you that the hydraulic conductivity in the west to east direction of deposition will be greater than the hydraulic conductivity across the width of the channel sand deposit. You are planning a 24-hour test in which you will measure drawdown at observation wells, and you want to determine where to place those wells. So you start with this layout, with 1 monitoring well in the aquifer near the pumping well, and 2 monitoring wells along an east-west line in the channel sands. You run the pumping test in your AEM model, in which you have placed some rough estimates of the hydraulic properties. You will measure drawdown in the model at the same locations you plan to in the field aquifer test to see how well PEST will be able to perform in estimating aquifer and sand deposit properties. PEST does a pretty good job. The PEST, aquifer, and sand hydraulic parameter estimates show the green bars are close to the known model inputs. But it has a bit of uncertainty in estimating the channel sand's longitudinal K, and even greater uncertainty in estimating the cross sands K value. This is because we have not provided PEST with much information in this direction across the sands. I tried a couple of different layouts to add observation wells across the sand deposit in different spacings, but it did not seem to help. Then I placed a 4th observation well here in the aquifer, between the pumping well and the channel sands, and fairly close to one of the channel sands observation wells. As the pumping test progressed in the model, and the cone of drawdown expanded outward, this additional well measured flow effects coming toward the center of the drawdown zone and from north to south across the sands. This allowed PEST to generate good estimates of the longitudinal and transverse sands hydraulic conductivity values with reduced uncertainty. So within a couple of hours, I was able to construct a simple model of this hypothetical site and apply PEST to help me design a pumping test with a number and location of observation wells that would effectively estimate the aquifer property values I was seeking. So to summarize, AEM models can be constructed very simply and quickly to represent key site features that you want to parameterize if you intend to develop a groundwater flow model for your site. And they run fast. PEST can operate on those models to show you how well your planned field program will allow it to estimate the parameters you are seeking. And it will assist you in refining your field program to produce a focused and efficient work plan that will help to ensure the success of the project.